Now consider a point in the scene, and let's say it's moving in some direction in the three-dimensional scene. That motion, of course, projects onto the image plane to create a motion on the image plane, which we will refer to as the motion field corresponding to that moving point. Unfortunately for us, there's no guarantee that we can measure this motion field. All we can measure is the motion of brightness patterns in the image, and that's referred to as the optical flow. So we're going to talk about motion field and optical flow, and when exactly is the optical flow equal to the motion field. So here is our scenario. There's a point in the three-dimensional scene P0, and its location is given by the vector R0 right here. P0 projects onto the point Pi via perspective projection, and its location on the image plane is described by the vector Ri. So imagine that the point P0 has some velocity in the three-dimensional scene. We'll say that that velocity is V0. So this point P0 in time delta t moves to this new location, which is given by the vector R0 plus delta R0. So the velocity of a scene point, V0, is the rate of change of this vector R0. So it's dr0 by dt. What we are interested in is the projection of this vector onto the image plane. And so in the image, we have an image velocity vi, which is dri divided by dt. That's dri. Ri is this vector right here, the projection vector, by dt. So we want to relate vi to v0, the image velocity to the scene velocity. So to do that, we use, once again, perspective projection. We know that perspective projection tells us that Ri, the vector Ri, divided by the effective focal length f is equal to R0 in the scene right here, divided by this distance, the depth of the point P0, which is R0 dot z, where z is the z-axis of the coordinate frame placed at the pinhole of the camera. So now, we want to find Vi, and Vi is dRi by dt. So we're going to find the derivative of Ri right here in the perspective projection equation with respect to time. We know how to do that by using the quotient rule of derivatives. That is, we say that dRi by dt is equal to f times the denominator times the derivative of the numerator, which is V0, minus the numerator times the derivative of the denominator divided by the denominator squared. This is the quotient rule of derivatives that you're familiar with. And this further can be simplified using cross products as follows. So we have here a simple enough expression that says that if you tell me where a point is in the three-dimensional scene, that's R0, and what its velocity is in 3D, then we can use this expression to figure out what the velocity of the point is going to be in the image, which is Vi. This Vi is the motion field corresponding to the moving point in the scene. This is what we would like to measure. Well, unfortunately for us, there's no guarantee that we can measure Vi, or the motion field. What we can measure, or hope to measure, is the motion of brightness patterns in the scene. So here you have two images which are taken by a moving camera. Some interesting things to note here that the motion of points between these two images depends on the depth of the point. This should be fairly obvious to you by now from our lecture on stereo. But these are the two images, and we would like to take a point, each point in the first image, and figure out where it ended up in the second image. That would be the motion field. But what we can do is we can simply take the pattern, the brightness pattern in one image, and see where the brightness pattern ends up in the second image. And if we have a successful algorithm for doing that, which is what we plan to develop, we can get a result that looks something like this, where at each pixel you have a vector which tells you what the optical flow at that point is. So the motion of brightness patterns is the optical flow, and the optical flow vector tells you, the length of the vector tells you how fast it's moving, and its direction tells you which direction it's moving in on the image plane. So, ideally, optical flow is equal to motion field, and often it is. Unfortunately for us, not all the time. So let's take a look at a few cases where optical flow does not correspond to motion field. Now let's start with this example right here. You have a sphere which is made of a single material, that is, it has the same reflectance properties everywhere. Let's assume that this sphere is actually spinning about this vertical axis that passes through its center, and it's lit by this light source. So you have some shading on the sphere right here. So since the sphere is spinning, obviously there is motion field, that is, physically points are moving on the sphere. However, there is no optical flow. All the images taken by a stationary camera are going to be the same, identical to each other. So here's a case where you have motion field, but no optical flow. Well, here is the other extreme, where you have a sphere that happens to be stationary. And let's say this time you actually change the lighting, you move the light source as follows. You simply swing the light source around, the light bulb, and what that does is that it changes the shading on the sphere. In other words, brightness patterns are indeed moving in the images that are taken as a function of time, but there is no actual physical motion in the scene. So here is an example where there is no motion field, but there is optical flow. So these are two sort of special cases that show that, yes, there can be optical flow and no motion field, or there can be motion field and no optical flow, but we hope that most of the time the optical flow corresponds to the motion field. Now here is an interesting example where indeed you have both optical flow and motion field, but they simply don't correspond to each other. This is called the Barber-Pole illusion. In this case, you have the cylinder that's spinning. Obviously, it's spinning about the vertical axis shown right here, this vertical axis. And we know that the motion is horizontal. That is, all points on the cylinder are moving in the horizontal direction. However, if you look at this pattern right here, and that's what you're capturing in the image, if you're capturing a video of this, you're capturing the motion of the pattern in the image. If you look at this pattern, that's actually moving in the vertical direction. So take a look at one of these stripes, and if I move my cursor down along with the stripe, you see that the stripe is essentially just sliding down. And therefore the motion that you end up measuring, that is the motion of brightness patterns, is perfectly in the vertical direction. So here's an example where you have both, but they simply don't correspond to each other. They're actually in orthogonal directions to each other. So this idea of incorrectly perceiving motion also applies to human beings. That is what's referred to as a motion illusion. So in this case, where we have the Dongory wave illusion, this is of course a static photograph, but if you move your eye around, you will see that these red leaves are in motion. They actually wave around. And obviously there is no motion here, so you have optical flow in your visual system, you're measuring it, but there is no motion field. Here's another very interesting example by Ouchi. It's called the Ouchi pattern. In this case, you have this little disc in the center with one pattern, and then an outer annulus with another pattern. And if you move your eye around, you'll see that the inner disc seems to be moving with respect to the outer ring. Again, that's an illusion. There is no motion field, but we are perceiving optical flow.